This video presents the paper entitled Co-Design Optimization of Morphing Topology and Control of Wing Drones, accepted for publication at IEEE ICRA 2024. Morphing drones are drones capable of varying their body shape, such as morphing their wings. The shape adaptation enables them to execute aggressive and agile maneuvers, making them more adaptable than conventional drones in complex, obstacle-rich environments. Designing morphing wings requires caution as it involves the integration of actuated joints. Actuated joints amplify the coupling between topology, aerodynamics, and control. Designers typically address this challenge through iterative processes that culminate in a final suboptimal design whose quality depends on the designer's abilities. A useful approach that can help the designer is to jointly solving hardware and control problems with co-design. Currently, there are existing works that co-design flying machines that determines the number of propellers, the position of the propellers, and the drone's shape. However, there is a lack of a feasible method for co-designing morphing drones because no existing approach combines aerodynamic modeling, shape-shifting surfaces, and motion intelligence. Our work addresses this gap by presenting a methodology to co-design morphing drones with shape-shifting wings. Below, you can see a co-designed drone performing a slalom maneuver while morphing its wings. Our co-design methodology requires the user to define mission scenarios. The methodology evaluates the drones using aerodynamic multi-body modeling and trajectory optimization. The parameter selection is done with a multi-objective optimization algorithm. The methodology yields a Pareto front of optimal drones that balance opposing objectives, such as mission time and energy consumption. From the Pareto front, the user can select the preferred conceptual design and continue the design process. The platform we consider is a winged aircraft with the left and right wings connected to the fuselage by a morphing mechanism, depicted by the yellow sphere. The morphing mechanism enables relative motion between the parts, as demonstrated in the video. The type of wing movements depends on the type of morphing mechanism employed. The platform does not have wing ailerons, tail rudders, or elevators, leaving only the actuation of the morphing wing to control the drone's attitude. The parameters optimized by our co-design methodology include wing chord size, wing span size, wing vertical location, wing horizontal location, wing orientation at its zero configuration, kinematic chain of the morphing mechanism, servomotor models, propulsion unit characteristics, and controller weights. To predict drone behavior, we modeled the drone as a multi-body system composed by three primary rigid links: the fuselage, the left wing, and the right wing. Aerodynamic forces and moments are identified by conducting aerodynamic simulations using the 3D uniform triangle panel Galerkin method with the software Flow 5. Aerodynamic forces are modeled for each single body, neglecting interactions among these bodies. The total force is computed using the superposition principle. Here are the equations of motion. In detail, the terms are inertia forces, bias force that accounts for Coriolis, gravity, and friction, aerodynamic forces, propeller force, and morphing mechanism torque. We use trajectory optimization to evaluate the desired actuation inputs for navigating the drone. Our actuation inputs are propeller thrust and joint torque of the morphing mechanism. The problem is formulated as a nonlinear optimization problem. The cost function minimizes a combination of time and energy consumption regulated by a weight parameter. Constraints are imposed to ensure adherence to initial conditions, hardware limits, obstacle avoidance, reaching checkpoints, integration of decision variables, and enforcement of system dynamics. We assessed our methodology by co-designing an agile drone capable of executing complex maneuvers. We chose 5 different slalom scenarios as mission scenarios. The output is a Pareto front that balances mission time and energy consumption. We conducted the test 9 times to demonstrate the repeatability of the methodology. From the 9 Pareto fronts, we selected 4 drones with different characteristics. Drones positioned on the left side of the Pareto front demonstrate higher energy efficiency, whereas drones located on the right bottom side exhibit lower mission completion times. To benchmark the co-designed drones, we compared them with the Bixler 3, a commercial fixed-wing drone equipped with control surfaces. The Bixler 3 drone shares similar weight and size with the co-designed drones, but is outperformed in both objectives simultaneously by all selected drones. The plots show the trajectories of both the Bixler 3 and the co-designed drone. The co-designed drones reach higher velocities, approach obstacles more closely than the Bixler 3, and consume less energy. Lastly, we tested the co-designed drones in mission scenarios different from the input ones. We created a parametric scenario featuring spheres as obstacles and 2 checkpoints. The scenarios vary in terms of checkpoint positions, sphere radius, and initial conditions. We varied the scenario parameters, obtaining 972 different scenarios. The results show that, in our tested scenarios, co-designed drones outperform the commercial platform in agility and energy efficiency. In summary, we have introduced a co-design methodology that proposes conceptual designs for morphing drones. A limitation of our approach is the aerodynamics model approach we used, as is valid at low angles of attack and neglects interactions among bodies. Providing a model that relaxes these assumptions would lead to a more realistic model. Regarding future work, we can focus on physical testing and expanding the co-design methodology to account for new parameters. Thanks for watching.